from my MSc. And when I asked Simon for suggestion on inviting someone as invited speaker who works in India, he polled the research community, and that was the unanimous choice. So very eager to hear this talk on entanglement and complete positivity, relevance and manifestations in classical optics.
Thank you very much. First, I would like to thank all the chairs and all the co-chairs of this conference for inviting me to give this plenary talk today. The so some of the lights can be dimmed. That's fine. No, I think it can be a little brighter, if possible. The mathematical structure of quantum mechanics uses many subtle features related to, that's fine, related to complex Hilbert spaces, linear operators, and maps. As we all know, for composite quantum systems made up of kinematically distinct parts, pure states are vectors in the tensor product of the subsystem Hilbert spaces. Typically, such vectors are linear combinations of product vectors, and this is the source of the property of entanglement. As a consequence, when the total system is in a generic pure state, each subsystem is in a mixed state. It should go to the next page. What happened? Oh, this one. Sorry, wrong button. Yeah. So, pure states of isolated systems, as we know, evolve in quantum mechanics via the Schrödinger equation. For open systems, it is necessary to describe states by density matrices, density operators, and to describe evolution by maps of density matrices onto themselves. The subtle concept of complete positivity, the CP property, arises in this context as a condition on evolutions which are physically acceptable. Suppose let us denote by this symbol, script R of the Hilbert space H, the set of all density matrices for a system based on the Hilbert space H, that is all Hermitian, non-negative, normalized density matrices. Then any map describing a possible physical evolution is linear in the density matrix, and at the very least it has to preserve the positivity of the density matrix and the trace of the density matrix. So this is, let me arrange my papers. This is given by the two conditions here. Starting with a rho which is non-negative and normalized to unit trace, the map omega must ensure that the image rho prime has those two properties. To this condition, natural condition, we add the subtle CP property, which says if you choose any second Hilbert space, script K, and consider the tensor product H cross K and the set of all density matrices on that product Hilbert space, and if you trivially extend omega acting on rho to omega times the identity on the second Hilbert space, this must also have the positivity property. It must preserve the traces and the non-negativity of density matrices in for the enlarged system. Now, this might look like a very innocent looking condition, but it is non-trivial precisely because in the tensor product Hilbert space there are vectors of the non-product form. And as you all know, in in practical terms, it is adequate to impose this CP condition for Hilbert spaces K not exceeding the dimension of H in forming the tensor product. So from the nature of the statements that I have just made, it must be obvious that we are dealing here with specific mathematical features of tensor products of Hilbert spaces and of certain operators and maps associated with them, which are independent of the physical interpretation we give to them. That is to say, entanglement and complete positivity by themselves are not intrinsically quantum mechanical in content. That is what I would like you to appreciate. And it is this that motivates the three examples that I will now describe, all taken from classical statistical wave optics in the Paraxial regime.
Sir, omega is a field so that we can extend it linearly to all.
Beg your pardon?
Omega is a field so that we can extend it linearly to
Omega, it's a map from density operators to density operators.
RH tensor K then.
So you trivially extend omega by taking the product with the unit.
So that we can extend.
I suppose so. Must be. You must be right. So, in the immortal words of Arthur Whiteman, my aim will be to inform rather than to astonish. The first example involves propagation of Gaussian beams and properties of some of these beams during propagation as signatures, robust signatures of entanglement. The Paraxial, I told you already that all the examples will be taken from the Paraxial regime. So the Paraxial wave equations in one or in two transverse dimensions, they are approximations to the three-dimensional Helmholtz equation, and if you have only one transverse dimension, this is the Paraxial wave equation. If you have two dimensions, this is the Paraxial equation, wave equation. So here the z-axis in space is the propagation direction, and you have a wavelength lambda, and lambda bar, like quantum mechanics, is lambda over 2 pi, and the wave number is the inverse of lambda bar. The most simple, coherent, and for simplicity centered one-dimensional Gaussian solution of the Paraxial wave equation can be easily set up. You start in what is called the waist plane, where it is at the narrowest situation. Let us say the waist plane is labeled by z equal to 0, propagation direction z equal to 0. So take the amplitude to be of this form, where w is the width in the waist plane and capital I is a measure of the intensity of the wave. Then from the wave equation you can solve for psi at x for any z, and it has a certain form which is given in equation 5, which is quite easy to understand. The various factors, let me just explain the physical significance of these factors. There is an exponent here which depends only on the propagation distance, independent of position x in the transverse plane. That is a famous Gauy or Gua phase. This is a French name, and we have difficulty pronouncing it. GUOY phase, which is more than 100 years old. Now, there is a nice way to rewrite this solution of the Paraxial wave equation in a more easily understandable form, for which we define relevant parameters. The first is what is called the Rayleigh range. It is the square of the width divided by twice lambda bar. Its significance will come out very soon. Then you have a width of the wave dependent on propagation distance, defined in this way. And a new parameter appears, which was not there in the waist plane, the radius of curvature at propagation distance z, which has this form. In terms of these parameters, the solution which was there in the previous slide, this last equation 5, has a more compact form. The changing width appears in the normalization factor. Here is the famous French phase. And then here is the Gaussian factor, x squared over z-dependent width squared, and then a phase term involving the radius of curvature r. In the waist plane, this radius of curvature becomes infinite. As you can see, z equal to 0. This is negative infinity. And the physical meaning of this Rayleigh range, a parameter here, is that it is the distance over which the width of the Gaussian amplitude expands by a factor square root of 2. So that is the operational definition of the Rayleigh range. The important point in this coherent or simplest case is that the rate at which the width increases during propagation is determined by this parameter Rayleigh range, which depends only on the width in the original plane, the waist z equal to 0. There is no other parameter on which this range depends. That's the important feature. Now you can generalize this pure case, you can say, to the partially coherent situation in one-dimensional, and we arrive at a family of two-point correlation functions which have been much studied over the decades, the so-called Gaussian shell model beams, and I use the short form GSM for them. Such a beam, a GSM beam, this is in one dimension, starts out in the waist plane with this structure which I have given in equation 9. Of course, this is the intensity dependent normalization factor out in front. This is the real Gaussian part, exactly as before. The new feature, because it's not a coherent but partially coherent beam, is this last factor term in the exponent, e to the power minus separation distance squared over twice delta squared. This delta is the new parameter which appears. So W, of course, retains the meaning of the waist width. Delta, the new part, the new parameter, is the so-called coherence length. The previous case, which was described up there, corresponds to delta being infinite. Now, this two-point function, given here for z equal to 0, evolves to a two-point function for all z. And how do you get it? You solve the Paraxial wave equation with respect to one variable x, and you solve with respect to the other variable x prime by the complex conjugate Paraxial equation, and then you get the solution gamma for arbitrary propagation distances. The important thing here is that now the Rayleigh range changes in its structure. It depends not only on the width at the starting point, but also over the coherence length. In the case when delta becomes infinite, this reduces to the previous definition, but you can see that for partially coherent case, the Rayleigh range is less than what it would be for the coherent case, smaller than in the coherent case. In any case, here is the solution for the two-point function for this partially coherent beam. I have all the expressions here. Here is the width as a function of z with the new value of the Rayleigh range. So once again, Z equal to ZR is the point at which W becomes square root of 2 times its original value. But I have also written it in more complete form here with all pieces explicitly shown, so that you see how this expression differs from the case of the coherent beam. Coherent case would correspond to delta equal to infinity, which means this whole thing becomes just unity. So you see here explicitly the change that has appeared because of partial coherence. Here is the behavior of the coherence length itself as a function of propagation distance. This also becomes root 2 times its initial value at Z equal to ZR, and here is the radius of curvature. So, to repeat, over a propagation distance ZR, both the width and the coherence length become square root of 2 times their initial values. So that is the physical meaning of the coherence length, Rayleigh range. So you see that in this case of one-dimensional GSM or Gaussian shell model beams, we have this physical feature. The fact that we have a partially coherent beam, which means that we have a finite coherence length delta, leads to a smaller Rayleigh range, which means to say that the width, for example, becomes root 2 times its initial value sooner than in the coherent case. Now, what we will do with this beam is the following. First, we generalize from one transverse plane to one transverse dimension to 2 transverse dimensions. So we take an initial amplitude at Z equal to 0 to be a product of 2 Gaussian amplitudes, but we choose the widths so that they are unequal. Let us say for convenience W1 greater than W2. So this is an anisotropic situation to start with. So you say that in the waist plane you have an elliptic amplitude and the principal axes are x and y. After free propagation, by looking at the expressions I have given in the earlier transparencies, you can easily convince yourself at any later point in the propagation direction z, this amplitude appears as a product of 2 solutions of the one-dimensional problem. So you have 2 of these French phases, and then you have the Gaussian piece in x, Gaussian piece in y, and then a complex piece coming from the radius of curvature, R1 and R2, R1 for x, R2 for y. Naturally, in this case, because we have an anisotropic situation, there are 2 Rayleigh ranges, Z1R and Z2R. Remember, this is a coherent case, so they are very simple in structure, width squared over twice the wavelength, lambda bar. And here are the various expressions for the Z-dependent width W1, W2, all explicitly given. As I said, we have 2 Rayleigh ranges, and the first one is greater than the second because the first width has been chosen greater than the second. Now, so it means that an anisotropic amplitude, the x part and the y part will expand at different rates. Thank you. Now let us look at this situation, this amplitude, in a rotated coordinate system in the transverse plane. This is a very simple operation. Let us switch from x and y to rotated x prime and y prime with an angle theta between them. On account of the anisotropy, if we were to write the amplitude psi of the previous transparency in terms of the rotated variables, and let's call it psi prime, this will no longer be of the product form in the new variables x prime and y prime. That is quite obvious because of the anisotropy. Imagine now that you measure intensities, widths, and the propagation behavior, the dependence on z, all in the direction x prime. You choose the direction x prime rotated from x by an angle theta, and you imagine making all measurements with respect to or in the direction, spatial direction x prime. To handle this, what do you have to do? You have to first construct the corresponding 2-point function with 2 transverse dimensions, as I have given here, psi prime, the rewritten psi, at the point x prime, y prime in the transverse plane, times psi prime at another point in the transverse plane, complex conjugate. Then what you have to do, if you want to limit yourself to measurements of intensity along x prime, you set y double equal to y single and integrate it away. Now you can easily see from the structure of these expressions, you can convince yourself this result, which is adequate for all calculating all measurements of quantities in the one dimension x prime, it necessarily has to have the form of the GSM beam, which I had shown in an earlier equation 11. It necessarily has to have this form. That is very easy to convince yourself. So, subject to that, you can calculate the width as a function of propagation distance. It's very easy to do it in terms of the what we would call in quantum mechanics in the language of quantum mechanics the reduced 2-point function. And here is what you find. The way in which the width in the x rotated direction, the way in which it evolves with respect to propagation distance. Here z is the propagation distance, and you see explicitly how it changes as you go along the propagation axis. So the main thing is to see how this compares with the partially coherent case. What you do, in the waist plane, you have z equal to 0. So the w prime at 0 squared is just w1 squared cosine squared theta plus w2 squared sine squared theta. And then the question is, how does this evolve with respect to z? And when you do the calculation, simple algebra, you find this result. The width at a general point on the z-axis, in the propagation direction, ratio to its initial value at z equal to 0, can be manipulated, easily rewritten, calculated. It has the z squared dependence which you expect, and here is the expression for it. If you then rewrite it in the form that you expect for a one-dimensional partially coherent beam, that is a one-dimensional Gaussian shell model beam, you find it has exactly the form that you expect in the case of a situation with a finite coherence length, with a finite value of delta. This is different from the coherent case. It shows partial coherence, and this is just because you have looked at variables x prime, y prime rotated with respect to xy. And the coherence length itself is explicitly determinable. It is finite precisely because you started with a situation which was anisotropic. We assumed the width w1 in the x direction was strictly greater than the width in the y direction. As a result, here is this expression for the coherence length in this x prime direction, which has a finite value. And what this example shows is that in the language of which we are all familiar with, there is entanglement in the variables x prime and y prime, in the rotated variables, and it is seen directly in the way in which the width of the beam measured along the x prime direction changes during propagation. So the presence of a finite coherence length delta, you can say the behavior of the width w prime with respect to z is an immediate and you can say tangible evidence of entanglement in this situation. So this was my first example. Now I go, so this was a case of a signature for entanglement in a simple optical situation. What I will go to next, my second example, is a study of beams of this general form, Gaussian shell model beams, and the relevance in their study of an interesting map which initially seems physically very reasonable but turns out to not possess the complete positivity property and the consequences for the physical properties of these beams. So here we start from the very beginning with a family of, well, let me start with the definition of the tentative operation, physical operation. You know that in one dimension, any two-point function has two basic features. It must be Hermitian, that is, under interchange of the variables, it must go into its complex conjugate. And the other part is that it must be positive semi-definite. Now, if you were to define an operation, capital omega subscript x, x referring to the one dimension here, corresponding to only interchange of x prime and x, if gamma is a physically acceptable two-point function, so is gamma tilde. So the properties of one-dimensional optical partially coherent beams are all preserved by this map omega x. So one would imagine, is this something that can be physically realized? Because in one dimension, it certainly maps allowed physical states to allowed physical states, allowed two-point functions to new allowed two-point functions. So the question now, in the spirit of the definition of CP map, is the following. Suppose now you extend this operation in this trivial way to two dimensions of the transverse plane. You carry out this operation with respect to x dependencies, but you leave the y dependencies alone. That is, you take a general partially coherent two-point function, xy, x prime, y prime, map it to gamma tilde obtained by interchanging only x and x prime and leaving y and y prime alone. The question that you would ask is this a physically admissible mapping, in the sense for all input physical two-point functions, is the result also a physical two-point function? Does it have all the properties of such a function, namely non-negativity and hermiticity? So I will describe the study of this function using as an example a class of beams which have been very highly studied in the literature for many years, the two-dimensional version of the old GSM beam. So for here, to define these beams, we have to set up a suitable notation. I will write the vector rho, two-vector rho, to be a general point in the transverse plane with coordinates x and y, and rho prime is some other point in the transverse plane, x prime and y prime. Then, the most general anisotropic GSM beam, abbreviated to AGSM, anisotropic Gaussian shell model two-point function. This was described for the first time by some of us in 1985, and the two-point function has the form I have given here in equation 26. There is a normalization factor, numerical part. Then there are two terms which describe the intensity distribution across the transverse plane. The third term describing the coherence properties, the partial coherence properties of this beam in the transverse plane, and then a phase term. Now, what are the expressions that appear here? There is a 2 by 2 matrix L, which is real symmetric in both these terms, a 2 by 2 real symmetric matrix M in the coherence piece, partial coherence piece, and then a 2 by 2 real matrix K in the phase term. So the main conditions, so these are all 2 by 2 matrices, real matrices, and the conditions that have to be obeyed to have a physical meaning are that L should be symmetric, positive, definite, M should be symmetric, non-negative, and on K there is no condition apart from reality, plus one more condition which I will come to very soon. So this is a family of optical beams in which there are 10 independent parameters. Apart from the total intensity I, which will not change and so which I will ignore, there are 3 independent parameters in L, 3 in M, and 4 in K, which is what makes these 2-point functions, partial coherent 2-point functions, a 10-parameter family. And as I already said, the matrix L describes the intensity in the transverse plane, the matrix M describes the partial coherence properties, and K is a phase. But remember, there is one more condition which L, M, and K must obey in order that this be physical, and I describe it immediately. It is simpler to go to the Wigner distribution description of this 2-point function gamma, and here is the standard definition. We define a 2-dimensional vector P describing, you can say, the direction of an optical ray. So rho is a position type, is the position, and P is like direction. So it is a dimensionless 2-component real vector, and the two together define, for this class of problems, a 4-dimensional optical phase space. Then the Wigner function, as a function of these 4 phase space variables, is defined in the way it is done in quantum mechanics. You start from the AGSM 2-point function, separate the spatial arguments, and Fourier transform with respect to difference between the 2 spatial arguments. And when all the dust settles, naturally the Wigner function has again a Gaussian form in which a 4 by 4 real symmetric matrix V appears up in the exponent, and its determinant appears in the front. What is this matrix V? This matrix is called the variance matrix for this problem. It's a real symmetric 4 by 4 matrix, and its simplest expression is in terms of the Wigner distribution. Here it is. It's the second order quadratic moments of the Wigner function integrated over the 4-dimensional optical phase space. Now I can state the one remaining condition on the matrices of this beam, which I had said must be obeyed to have a physically acceptable situation. And that is described by what is called the optical uncertainty principle. And it says this real symmetric 4 by 4 matrix V plus I by 2 lambda bar times this numerical matrix beta, which is anti-Hermitian, this must be non-negative. This whole matrix on the left is Hermitian, and the condition on the variance matrix, namely on the parameter matrices L, M, and K, is that this optical uncertainty principle must be obeyed. Then and only then is our 10-parameter beam a physically acceptable beam. Now, for illustrating the relevance of a non-CP map, we don't need to deal with the full AGSM family. I gave the description just to tell you that there is such a family. We will be interested only in a sub-family in the large 10-dimensional family. This is what we have called a twisted Gaussian shell model, or TGSM family. This is something that Simon and I started studying in 1993, that's 20 years ago. It is quite simple in algebraic structure. The matrix L determining the intensity distribution is a multiple of the unit matrix. The matrix M determining partial coherence is also a multiple of the unit matrix. It is a phase matrix K which has a somewhat novel structure, and here I have written it in terms of Pauli matrices. So for this family of beams, here is the corresponding two-point function. Every piece is recognizable from the one-dimensional case. The really new feature is the existence of a phase in the last term. And this is what we have called the twist phase. And it is quite surprising that for such a long time, this phase had not been explicitly recognized. So then you can ask, just one moment, I think I've missed a page. What is the consequence of the optical uncertainty principle? Incidentally, in passing, let me mention, this is the most general beam you can consider in two transverse directions, in which it is Gaussian, it is naturally Hermitian in the exponent, and it is invariant under proper rotations around the propagation axis. The important feature is that such invariance permits the presence of this phase, the twist phase. Now the question is, what is the condition arising from the optical uncertainty principle? So you put all this L, M, and K, compute the matrix V, work out this condition, and you find here is the condition on the twist parameter. It cannot be chosen as large as you wish. It is limited. It has an upper bound determined by the coherence properties. This is a non-trivial condition. This is something that made this family of beams quite novel at that time. So this is one 4-parameter subfamily in the large 10-parameter family. Now I describe another 4-parameter subfamily. We have called it gamma superscript curvature. You'll see immediately why. It is defined in such a way, it is chosen in such a way that if you were to apply formally this mapping omega x extended by the trivial mapping in Y, you would get the other TGSM family. So the change is only in the form of the phase part. So L is the same as before, M is the same as before, K has a different structure. And what does a beam itself look like? Here is its two-point function. Everything is the same as far as the width and the coherence length go. It is only in the phase that you have very different looking expressions. And now you find that the optical uncertainty principle places no restrictions on the parameters of this 4-parameter family. You can choose any value you like for the U parameter in this expression, any value for R, and it's a physically realizable beam. Now you see what is the connection. How are these two subfamilies related to one another? And this is where the idea of a complete positivity or its absence makes its usefulness apparent. If you look at parameter values of the twist obeying the optical uncertainty relation, in that regime you find your extended map omega x cross identity will take gamma curved into gamma TGSM. Similarly, it will take gamma TGSM, the twisted beam, into gamma curved, which means in this regime, this is a physically acceptable map in the sense that it maps physically realizable states into other physically realizable states. On the other hand, if you were to go outside this range where the TGSM does not exist, here is what you find. Your extended map acting on this physical state gamma, two-point function gamma curvature, is unphysical. What is the meaning of this? Well, here it is immediately easy to see that if you combine the expressions I just gave with the famous theorem of 2000 of our illustrious co-chair proved in this institute, you see immediately the following results. Within the range where TGSM beams make sense, both of them are separable. Outside this range, gamma TGSM does not exist. Therefore, the gamma with the curvature, which is physical, is going to be non-separable. Now, this fact that the TGSM beam, which we defined in 1993, is separable in the usual sense, was proved very soon after by a group in Rome. I forget the name first. Ambrosini and Gori and company. They followed up our work very quickly and showed that the beams that we had defined have the separability property. It is fair to say that it is only now that we understand the separability property in a much more fundamental way, using these ideas of CP maps, non-CP maps, and so on. Okay. So this was my second example. Now I come to the last one. The two examples I have described up to now were both taken from the regime of scalar wave optics, in which you ignore the polarization property of light. Now I bring in polarization and show you again what you may call the power of entanglement. Now this is a problem which Simon has been concerned with for more than 30 years, at least 31 years, because when he joined me as a student in 1980 or 81, you showed me this work in 1982, I think, or it was published in 1982. So polarization, what I will describe now, has been on his mind, has been weighing on his mind ever since then. So for a strictly plain electromagnetic wave, omitting the standard factor, you know that pure polarization states correspond to specific electric field vectors in the transverse plane. They are constant because you have taken out the propagation factor. So E is a vector in a two-dimensional complex Hilbert space. Intensity of the beam wave is essentially E dagger E. The polarization property of such a wave is computed, is described or pictured as 1 by the intensity E dagger Pauli matrices E. And this gives you a unit vector on the sphere S2, the Poincare sphere. Here, the notations or the conventions for Pauli matrices in optics, polarization optics, are different from the ones in quantum mechanics and particle physics. So just in case somebody here is seeing this for the first time, I have given the convention, the connection between the two conventions. So a fully polarized plane wave is describable by an electric field amplitude, two-dimensional. If you have a general polarization state, mixed state, then it is described by an ensemble of electric fields, and naturally, since you have to take ensemble averages, you replace the first description by a description involving what is called the coherency matrix phi. It is the ensemble average of E dagger, so it's a two-dimensional Hermitian non-negative matrix, and the intensity comes out as basically the trace of this matrix, and the determinant has to be greater than or equal to 0 because it is non-negative. The subset of these mixed polarization states, the subset which corresponds to pure polarization, in which you can say if there is any fluctuation, it is only in the intensity, this corresponds to vanishing determinant of phi. Then phi has the form I have given here, where gamma, so this goes back to the Poincare sphere description in this subclass, pure polarization states. In the language of this coherency matrix phi, which describes the most general polarization state, it is useful to rearrange it, the 2 by 2 matrix, to rearrange it as a 4-dimensional column vector, and this is just the definition. It's a matter of convention. And it will be useful, as you will see very soon. Finally, there is one more way in which the polarization state can be described, and that is with the Stokes vector. That's a real 4-dimensional vector, and that is defined as trace of the Pauli matrices with this 2 by 2 coherency matrix. A runs from 0 to 3. Tau 0 is a unit matrix. So once you have the Stokes vector, you can reconstruct phi, and here are the properties connecting them. So from the physical point of view, the important thing is that in the Stokes description, in the Poincare description, it is a unit, the point on the unit sphere. In the Stokes description, you have the result that the Stokes 4 vector must lie on or inside the positive light cone in this artificial 4-dimensional space. If you lie on the light cone, it goes back to pure polarization. If you are in the interior, it is mixed polarization situation. So to sum up, well, there is a way also to connect these various descriptions. You can go from the Stokes description to the coherency matrix description. It's a very simple numerical matrix. So to sum up, while a pure polarization state is determined by an electric field vector, a 2-dimensional complex amplitude, a mixed state can be described in 3 equivalent ways with simple relationships, either the coherency matrix, which is 2-dimensional, or the same thing rearranged as a 4-component vector, or the Stokes vector. Now, what are the physical systems which can act on the polarization state and preserve the basic properties? The simplest are so-called deterministics or Jones systems. They are physical systems which act directly on the electric field 2 vector and go from a vector E to E prime by some 2 by 2 complex matrix. If this is the way the electric field transforms, you can immediately read off the effect of a Jones system on all the ways of describing a general polarization state. Here is how phi would change, here is how this column vector would change, here is how the Stokes vector would change. In the case of a Jones system for algebraic work, while here we think of it as a 2 by 2 matrix, we can also rewrite it like a 4 by 4 4-dimensional column vector in this way. So in the last equation. So the main thing is that, Jones, what happened? Jones systems or deterministic systems are defined by their action on the electric field directly. Beyond this, you may have non-Jones systems, and these are the famous Mueller systems, Mueller matrices. Their action is given not on the electric field, but action directly on the Stokes vector, or you can say directly on the polarization state. So a Mueller matrix, capital M, has such an effect on the Stokes 4 vector, S prime equals ms, which can be translated into corresponding actions on phi, phi tilde, as I have written here. These are simple matrix transformations. In particular, the change in the coherency matrix can be written. This is what is very clever, done in 1982. That you can express the new coherency matrix in terms of the original one in a certain transformation, through a certain equation, which brings in a matrix which has the hermiticity property. So this was a very, very clever way of rewriting some of the equations I have given earlier. So as I said, this Mueller matrix M is real 4 by 4. With it, you are able to associate a 4 by 4 Hermitian matrix. Now, the minimum condition on a Mueller system to be physical is that since a set of all states is defined by the light cone in this 4-dimensional space, it must map the light cone along with its interior onto itself or into itself. So this is the minimum condition. But as we will see very soon, there is something more. Now, in case our Mueller matrix arises from a lower level electric field vector description, namely from a Jones system, here are all the expressions in terms of J. So this is very easy to arrive at. So now we can see this is something that had been proven by Simon in 1982. A Mueller matrix arises from a simpler lower level Jones matrix if and only if this Hermitian H of M is essentially a one-dimensional projection. And you can see that from this expression. Suppose, on the other hand, you had an ensemble of Jones matrices, Jones systems, then that is also physically realizable, and that would correspond, by looking at these relations, to this Hermitian matrix being positive semi-definite. So this language describing Mueller matrices in this way through Hermitian matrices and their positivity properties was a very important step in the early work. At this stage then, let me tentatively define three sets of Mueller matrices in the following way. The first one is the obvious geometrical description, the set of all matrices which maps the light cone plus its interior into itself or onto itself. So tentatively, let us say this is the largest set of matrices that could in principle be physically realized. Now next I define M physical as all those Mueller matrices which are in fact physically realizable, and at the moment I am not even able to say exactly what it means, but we will see the answer very soon. And then we take as the definition of the third set of matrices M plus, which are all convex linear combinations of M's which arise from ensembles of Jones systems. So you have these inclusion relations. M plus is the smallest one, M physical, which is yet to be pinned down, stands in between, and script M is the largest of these sets, and in any case there can be nothing physical outside of script M. So for a long time the question was, what exactly is the set of physically realizable Mueller matrices? Is it as big as M, or is it as small as the smallest of these three? Is this equality true? Now this seems like a somewhat simple problem, but it is quite delicate and it required quite a lot of effort to arrive at the solution. I might say in passing that the full description of the set M, set of all Mueller matrices which maps the light cone plus its interior into itself or onto itself, the full description of this was, I think, obtained by the group in Mysore, worked Gopal Rao, Mallesh, who else? Yeah, fine. And who else? 2, 3. So this is done sometime in the 80s, 90s, 90s. So that's quite remarkable that by using group theoretical arguments, they were able to pin down the structure of the set M. But this was no proof that all matrices in M are physically realizable. To answer that question, it has turned out one has to appeal to the ideas of entanglement. So this is the power of entanglement in the realm of polarization optics. What one has to do, up to this point we have talked of plane electromagnetic waves, that is fixed propagation direction and the polarization given by a constant electric field vector. It now turns out if you go from plane to paraxial waves, you replace a constant two-component electric field vector by a field vector of two components where both E1 and E2 vary in some way in the transverse plane. So what are these elements of? they are elements of the two-dimensional complex space times square integrable functions on the transverse plane. So this is where the tensor product appears when you generalize from plane to paraxial waves. The simple 2 by 2 coherency matrix, ensemble average of E dagger, is replaced by something which depends on a pair of points in the complex plane. And here are the expressions. So now the properties of this phi, which varies across the transverse plane, they are more specific. Apart from hermiticity, they have this non-negativity property. Now, to cut a long story short, what happens is that if you impose these conditions on a Mueller matrix acting on a paraxial wave, you get new conditions on physical acceptability. And while all the expressions are available and they will be on YouTube, I have just signed the form a few minutes ago, so I will not go into details. You find that by cleverly choosing a particular entangled expression describing entanglement for the electric field vector in the transverse plane, you are able to pin down the set of all physically realizable Mueller matrices. And lo and behold, what happens is that in terms of the three spaces I had defined earlier, the physically realizable Mueller matrices are exactly the ones that come as convex ensembles of Jones matrices. I just show you. This had been a conjecture that the set of physically realizable Mueller matrices may be this set M plus, which is all convex linear combinations of Jones systems. Now, by using this technology of entanglement, it has been possible to prove it, to pin it down, and to show that this is indeed so. So I will stop at this point. I have arrived at my destination on time. I will just say that I hope the examples that I have presented to you bring out the relevance and the usefulness of concepts like entanglement and complete positivity, or better, in our example, the lack of complete positivity in the classical wave optical situation. They certainly provide new insights into old and well-established phenomena. So my last sentence would be, if there are any classical opticians in the audience, I suggest to you, open your eyes wide, wipe your spectacles clean, and look carefully at these ideas. Taken from quantum information science, you may find them useful in your own work in classical optics. So my thanks finally to Simon Chaturvedi and Krishna Kumar Sabapati in the preparation and presentation of this talk. Thank you, and I am ready for the shawl. It's not a question, a comment, maybe.
Yeah.
Is there any, equivalence between your M being equal to M plus, and what is its implications for quantum information in terms of the language of states and so forth? Is there some?
All I can say is that which will produce that kind of effect on the Stokes vector. So it has nothing to do directly with information in that sense. It's a very concrete physical property. You just write down, I think the standard classic example is a paper based on analysis of some experiments in polarization optics, and they had tried to obtain a Mueller matrix from the data and presented it as an example. It turns out it is not physical. And the people who did that work did not have this insight. They must have thought that we have done an experiment, we have taken the data, we have computed the Mueller matrix from it. It must be physical. Unfortunately, it is not. So this sharpens the condition. When is it physically realizable? That's the best I can say.
Thank you. Any other questions?
Yeah.
Thank you again. So if there's no further question, let's thank the speaker again. And since he said that he's ready, I'm ready too.
Yeah.
It's a very, very great pleasure to offer you this shawl.